This is an A-level maths pure paper from Pearson Excel. It's October 2021. Except I've already done this paper on this channel here. So there's going to be two instructions for this video. One is get 100%, and two is send every single question to the head examiner. Now, what do I mean by that? Well, usually examiners will mark your paper, and they'll have the mark scheme which looks a bit like this in front of them. And essentially, if you do anything that's not in their script, they have to send it to the head examiner. And the head examiner will have to look at it and they'll have to decide how many marks it's worth, if any. So essentially, what I have to do here is avoid anything that's been written down on the mark scheme for each question. Now, if the question is on multiple parts, I only have to try and get one part of it to be sent to the head examiner, because then the whole thing will be. And of course, lots of parts are just one markers to write down the answer, so I can't do it for every little bit. But yeah, let's see, is it possible to do an A-level maths paper and have every single question sent to the head examiner? Is that possible? Let's find out. So the first question is quite hard. It's quite a difficult start, because the simpler the question, the harder this challenge is. Because like there's just an obvious way of doing this, right? You do f of 1 equals 0 and you solve that equation for a and you get the answer. The other reason this is hard is because the mark scheme is actually pretty thorough on this question. It talks about polynomial division and setting the range to 0. It talks about comparing coefficients when you do some kind of factorization. It even talks about some kind of trial and error method that I didn't really want to bother to understand. So the first question immediately took a little bit of imagination, but got there eventually. What we're going to do is we're going to set f of x, which is this, equal to some function p of x times x minus 1. This is what it means to be a factor. Of course, it's just this times some other thing. So that's cool. Now, p of x needs to be a quadratic, which I'll call this, because, of course, a quadratic times a linear thing makes a cubic. Now, of course, if you set x to be 1 here, and of course, actually, what I'll do first is I'll differentiate this, and I'll differentiate it again. And then I'll take f of x, and I think I'll differentiate that, and then differentiate again, and then differentiate again. And you'll see where I'm going with that. If you set x equals to 1 here, you just get factor theorem. You just get f of 1 equals, well, when you put in 1 minus 1, this goes away, and you just get 0. Now, I can't use that because that's on the mark scheme. But if you differentiate this to get f dashed equals, and now you're going to have to use some product rule here, p dashed times the derivative, sorry, leave this one alone. And then this derivative is just 1. And so you leave this one alone and you get this. Now, when you plug in x as 1 here, you get f dashed of 1 equals, now this goes away because 1 minus 1 is still 0, and you just get p of 1 over there. Now, p of 1 is just b plus c plus d, and f dashed of 1 is just 3a plus 20 minus 3a, which is just 20. And we end up with this equation here, which is good. We're going to differentiate this again because this is clearly not enough information to answer the question. So let's differentiate this again, use more product rule, differentiate that one, leave that one alone, differentiate this one, leave that one alone, and then differentiate this one. These two can come together. And now, again, just put in 1 into this. Put in 1 to this, this cancels with, this goes away. So you get f dash dashed of 1 equals 2 lots of p dashed of 1, which we can plug into these things here. So putting 1 here, you get 6a plus 20. Put in 1 there, you get 2b plus c, times by 2 is 4b plus 2c. So that's good. One more time, let's differentiate this. Again, just using small product rule, putting in 1 again, because why not? And then putting our systems here. Now, neither of these actually depend on 1, so that's cool. 6a equals 2b. Sorry, 6a equals 6b, because you times this one by 6, by 3 here, which means a equals b. So let's replace these b's with a's, because we're told that's what they equal. And of course, these b's, if they're actually 4a, can swing over to here and you make 2a over there. So that's what I've done there. And next, I think what I've done is I've said, well, in the initial condition, we can write f of x, which is this, equal to p of x, which is this, times x minus 1. So this is just this written out more fully. We can clearly see that d times minus 1's got to be minus 4. So therefore, d is positive 4, because two negatives are multiplied. Sorry, because positive times negative makes negative. And so therefore, if d is 4, I can plug that into there, take away 4 from both sides. And then I think we're good to go. This is just a simultaneous equation. So we can just solve that. I think I just replaced this c with 16 minus a, multiply out, and solve for a as 3. And we'll finally get our answer in hopefully a way that will have to be sent to the head examiner. Question number 2 then, very prescriptive again, so hard to get this sent to this head examiner, hard to come up with anything that will work here. But what you could do is you could differentiate this, so which is that. Of course, the turning point happens when f dashed is 0, so we'll set that to 0, solve for x as 2. If we put 2 back into here, we find f of 2 is 1, which means this has a turning point at 2, 1, which actually answers this question at the bottom here. The answer is 2, 1. But more importantly, if we draw a graph, the turning point is 2, 1, and this is a quadratic. Now we know the original, the true quadratic is y equals x squared. It's just on the bottom here. And now all of this quadratic here is just this one shifted, what is it, 2 left and 1 up? Sorry, that's right, isn't it? 2 right and 1 up, which means it's just a graph transformation g of x minus 2 plus 1. So of course we put x minus 2 in here to get x minus 2 all squared, and then add 1 to it, and that'll be f of x. And so there we've written it, and so we have this first bit done. The coordinates of p where it hits the y-axis will just when y is 0. Again, there's no way you can do that to get it sent because you get the mark for just writing that down, and likewise here you just get the mark for writing that down. So good, we're good to go. Question number 3 then. The first bit I tried to play around with some way to use this, but completely wrong and backwards. But in the end, I just ended up doing what the mark scheme says because I think I have a way of doing the next bit requiring to get sent. So I'm just doing this in the normal way, right? You put u1 into here, which is 2. You get this. You put u2 into here to find u3, and then you get this. You put all of those things into there. You get this, you do some stuff, and you get the thing. It's all really boring. It's not really the point in this video. It's the next bit that we can do, solving this quadratic. So there's lots of ways to solve quadratics, including just pretending the solutions are of the form alpha plus root plus minus root beta. And then if you do that, if you just assume this is what the solution looks like, it turns out that minus 2 alpha is equal to this number here, and alpha squared minus beta is equal to this number here. So of course, solve for alpha right away here, and then put that into there to solve for beta. And we get beta as this, and then put both results into there. You could, of course, root this one, which is quite nice. You can collect these together, and you get your 2 answers. This one is not an integer, which I earlier said it needs to be. So we'll have the answer of 6 here. Find the value of u3, where you just put your result of 6 into here, and you get u3 is this thing here. Not allowed this answer, I guess. Okay, so hopefully that got sent with all this nonsense here, but again, it was quite a hard question to do it for because it was just a very straightforward question. When we get to the later questions, like starting here maybe, it becomes more and more easy to come up with the answers to this video or the ways that we're going to do it because more complicated questions are actually better if you're doing this. So anyway, let's do this one here. So, okay, well, we're talking about turning points, so it's about differentiating this. It seems to me the obvious thing to do would be to write x squared as log of e to the power x squared because these would cancel, so that's good. But of course, now we've got 2 logs added together, so we can multiply the inputs. So that's great. And then when we differentiate a log thing, it's f dashed over f, right? Or g dashed over g if you're going to write it like this. So the differential of f here is going to be the differential of this, which we'll need more product rule for. So this derived, leave that alone. And then, which is 2x times this, of course, and then leave that alone. And then leave this alone and derive this. And then just put what was originally in there on the bottom. We can set this to be 0. If we're looking for a turning point, of course, the denominator is not going to matter anymore because we just want the numerator to be 0. We can factorize out e to the x squared. E to the x squared is never 0 across the real numbers, so we just need this bit to be 0, which we can do fairly easily, and we'll end up with the qubit that they wanted us to get. It's very hard to do anything interesting with the rest of this because it's just using a calculator and putting the iterative thing in there, and it's really, really boring, so we're not going to bother. I'm just explaining here that if one of them is below the line, one of them's above, then the root is somewhere in between. It's really boring. Don't bother with any of that. Again, so we've got a very prescribed thing to do here. It's just this times 1.8 to the power 2. So we get this. Now this is the bit where we could maybe do something a bit strange. Notice how it's power 2 because it's 20,000 in year 1. So actually year 2 just times by one of these, and then to get to year 3 times it by another, and you've already done 2 of them. So we're going to use n minus 1 here, and we want that to be bigger than 65,000. Now, of course, the usual way of doing this would be to take the logs of both sides, and that's what the mark scheme says, is do logs. We're obviously not going to do that because we can't. This one took a fair bit of imagination, but what we're going to do is we're going to write this as 1 plus 0.08. And now, this is a binomial, right? So I don't know what n minus 1 is, but we can expand any binomial, right, by using the formula that's in the book. It's in the formula book when you've got n, not an integer. So we can just do this. Now, the thing is, way over here, look how you're doing cube of 0.08. And also the factorial on the bottom of it is also getting bigger, which means I think I could just ignore, well, I can probably ignore anything after this term because it's really small, right, I think. And I think I'll still be accurate enough to get the correct answer. So I think I'm just going to cut these terms here and look for the answer to this. Of course, now here I've just typed in a bunch of these numbers. To get all of this, I can collect all of that together and times across like this, and then I can collect that together. I can put that in the calculator, and thankfully, this seemed like a pretty good piece of logic because this is very close to what you would get if you did logs, and you have to round up to the 17th year anyway. So I'm pretty sure that's all fine to do, and we're good to go there. So yeah, I think that's fine. Year 17 is the answer. This I couldn't think of anything to do interesting here. You're just timesing by 1.0 each time to get to the thing. So when you add them all up, it's just adding a geometric series. You have a formula for that. So we'll skip all this because none of it's very interesting. You just get the answer that they wanted you to get. Maybe you could literally just write out all 20 years here and add them all up, but I don't think that would be worth sending to the examiner. There's probably more interesting things you could do, but I thought I did something interesting enough here such that this question has already been sent, so I didn't really need to do anything for C. Anyway, number 5 then, this video is taking a lot long. Sorry, number 6, taking a lot longer than my videos usually do, doesn't it? A to B is this, and B to C is that. What I decided to do, well, I mean, firstly, A to C, there's no interesting way of doing this. I don't think you just do this one plus this one, and you get this. Let's find a bunch of lengths here. So do some Pythagoras on all 3 of these things, and you get some lengths here. Show that cos of this is that. Now, of course, you're supposed to do inverse cosine rule to get this. That's not what I'm going to do. What I'm going to do is I'm going to say the area of this triangle is half of the cross product of these two things. Now, I've used the positives because I know if you just use positives in cross product, it just makes the answer negative. You just get -1 lots of the answers before. But of course, you take the modulus. I should have put modulus in here. You take the modulus anyway. And so it doesn't matter if you have a negative. So anyway, the area is this. I've put this parallelogram in here because for those who aren't aware, finding the cross product of these two things finds the area of the parallelogram that the two vectors span. So if you just halve it, you'll get the area of the triangle. Anyway, to find cross products, you transpose these two vectors across like this. You put ijk at the top. You find the determinant of this matrix here, which is why the negatives don't matter because, in fact, you find, the negatives don't matter because you're just going to do Pythagoras at the end anyway. So of course, 4 times 4 minus 5, and then so on, you get all this. This needs to be a minus, remember, in here. If you know your cross product, you get this. Like I said, do some Pythagoras here. That's why the negatives don't matter. You get this. That's the area of the triangle. But of course, the area of the triangle is also half AB sine C. And of course, I'll use this as my A, which is this one. And this is my C, which is this one. So, okay, I can set these two things equal to each other. The halves cancel, divide by the surds. You get sine is this thing here. And now we can use sine squared plus cos squared equals 1. So we can do cos squared equals to 1 minus sine squared. Square this, you just get rid of all the square roots. Move this over, you get this. Amazingly, that turns out to be that. You square roots and you get exactly the answer, except you end up with plus minus. So for our final mark via this method, we're going to have to explain why it's plus 9 over 10 and not minus 9 over 10. And the answer to that is, if it was, you think of the cos graph, cos is negative between 90 and 180, or pi over 2 and pi if you're being grown up. So if it was cos, if cos was minus 9 over 10, the angle would be big. And if the angle in the triangle is big, that means the side that's opposite it is also big. Like if it's bigger than pi over 2, this is the longest side in the triangle. But it's not. That's actually the shortest side of the triangle. So this is an acute angle, and so therefore this is positive 9 over 10. And that explanation will get us the marks. Just before I do this question, I'm going to need to explain just a tiny bit about what I'm going to do here. If you have a really simple question like this, find the equation of the tangent line to this circle at this point. Now, the answer to this question is, well, here's two x's, right? X times x, and here's y times y. Replace one of those x's with 3, and one of the y's with 4, and that's the equation of the tangent line. That is just a thing that works. I might link a video below of me explaining that in more detail. I'm going to use that fact in this question. So, of course, the first bit, I'm just going to complete the square and do very boringly, and we'll get the answers here, so that's fine. This bit's the bit that we're obviously going to pay attention to. The line of that is the tangent. Now, bear in mind what I just said, right? I have this cheap way of finding the tangent, so that's what I'm going to use, right? So if we imagine that the tangent is tangent at some unknown point a, b, if I take this equation of the circle and just replace one of these x's with a and one of these y's with b, that will give me the equation of the tangent. So this here, I've just written this out with the two things and then replaced them with a and b. That's the equation of the tangent, which I can simplify up. Eventually, I'll end up with this in y equals mx plus c form. But of course, if I'm given this is the tangent, I can just compare some things. I can say that this thing here is equal to 3, and I can say that this thing here is equal to k. Now, this thing here I could have got just by doing a gradient like this, and doing, I know that this gradient is 3, I can do negative reciprocal for this radius, but it's quite interesting to just get it this way anyway. And this I do need, so this was worth doing because I get this, which is very helpful. Now, I've got 3 unknowns here, a, b, and k, and only 2 equations, so I need a third equation, and I'll get that by just putting a and b into the original equation up here. Actually, just like I did up here, but just using it in a slightly different way. Here's another equation now with a and b. Because I know the circle goes through AB, so this must be satisfied. I can use these 2 equations to solve for A and B, and I can put those results into here to find my K. So that'll be my entire plan. It's quite boring from here. You just rearrange this. You square everything, is what I did at least, which gives you this term. So you can put that into here, and then you solve this for A. It's all very boring, and you eventually get A as this. You could solve this quadratic in an interesting way if you wanted to, but I think we're being interesting enough as it is. And I've got another quadratic solve later, which I will do in a more interesting way. We get this for b, I guess, just putting it into there. We get b as this. And of course, we put both those results into here. You type that bad boy in the calculator, and you get k as this as your final answer, or 2 of your final answers, I guess, there. Good. Question number 8, then. So starts, I mean, we can't do anything with these 4 marks. When t is 0, you just get n equals a, which means a is the starting population, of course. And then when t is 5, n is double what a is, so you just solve that. Maybe actually there was an interesting way of doing this, but anyway, I'm going to do stuff here anyway. Find the rate of increase of the number bacteria 8 hours into the study. So I've written k as this, and I'm going to put that into here to find this. But of course, this e and this log can cancel, because I could write this t up like this, because of course this times this would give me this. But this e and this log can cancel, so it's just this. This is 2 to the power of 5th, and then t can just multiply down here, and we end up with this equation for n, which has not got an exponential. Well, it has got an exponential, it's not got e in it, which is quite cool, because now I can think about deriving this, but I'm actually going to be much more interesting than that, because I need this sent to the examiner, obviously, the head examiner. So I'm going to take log to base 2 of both sides, which is cool, right? Because this is a product, so I can separate that product out like this. This is just a constant, which will be very helpful in a second. This comes down to the front. Well, actually, log to base 2 just cancels, doesn't it? So that just all goes away and we get this. Now, the reason that this is quite helpful is because if I differentiate now, this is a constant, so it goes away, and this just derives to a 5th. So that's quite helpful. Now, what does log to base 2 of n differentiate to with respect to t? Well, remember, n itself is a function of t. So I'm interested in deriving both sides with respect to t. This just derives to a 5th, like I've said. Now, what does that differentiate to there? Well, I think this is non-A-level maths, I think. It might be. You could prove it using some A-level chain rule and stuff. But I don't think it's an expected result, which is why I'm leaning quite hard on it. So, okay, log to base r of f of x is f dashed of x over f of x, just like it usually is, but with and also a divide by log r here. And this log is the natural log. I write the natural log, sometimes I write as ln, and sometimes I write as log, depending on whether I'm concentrating or not. When you're at university doing maths, this is the natural log, so to me it's very natural to do that. But I mean ln if you're, I mean these two things are the same thing. I never do log to base 10, so if you ever see this, I mean log to base e. Anyway, so we have this here. This is quite cool. So this here is going to differentiate to the derivative of n divided by n times log of 2. So that's all quite cool. Cross multiply that over there. And yeah, this is good, because now I can just put this n that I found earlier into here and evaluate it. T is 8, and we'll get n dashed at the time is 420 to 2 sig figs. And the last bit I could have done, I think, in a more interesting way, but I chose not to. I just put the k's in as decimals and did the normal thing to solve these. I think it's pretty normal anyway. I feel like this question's already been sent, so my job was done. And I have a lot to do here, so I think I was fairly lazy on that second bit of the question. I'll leave it as homework for you guys to figure out how to do this in a more interesting way, or find your own interesting way of doing it that is quite nice. Anyway, question number 9, how do you do partial fractions without doing partial fractions? Because obviously I'm not allowed to do that. Well, you just be a legend instead, because it's actually pretty easy. What you do is you start with the correct thing, and then you say 50x squared. Well, that's just 25x squared plus 25x squared. And 38x is just 20x plus 18x. And 9 is just 4 plus 5. I mean, that's, I think, a fairly obvious first step to do. The reason that I've done that is because if I look at these first 3 terms, I think that factorizes perfectly to 5x plus 2 all squared. And now when you look at this thing, well, this here, I mean, this is just 20x minus 2x, and this is just 4 plus 1. I mean, we all went to primary school, so this isn't too hard. But when we look at these 3 terms here, That's just 5x plus 2 all squared. And now this is just 2 lots of 5x plus 2 all squared. And then this is just minus 1 minus 2x. Sorry, plus 1 minus 2x. And perfect. I mean, when you're adding two things in a fraction, you're allowed to split that fraction halfway down and say it's this, because of course the denominators are the same, so we could just combine these things together to make this. But of course now this cancels with that, and this cancels with that, and you're left with this. And yeah, that's done. B is going to be 1, and C is going to be 2. And we could also write this as like this, and then we show that A is 0. Because of course we don't need any of it, so A is 0, and we're done. Use binomial expansion to show this in powers. I mean, I can't be bothered to do this because this has been now sent to the examiner, so that's good. This is going to be done in the normal way. You just do this, you use this formula, which we actually used earlier, remember? You can factorize out the 5 from here, sorry, the 2 from here. Yeah, of course, to make this a 1, because it needs to be. I'm also going to swap those around, I think, as well. Like this, 2 to the power minus 2 is a quarter. This is all really boring. You just look for the expansion. You just do it. You collect everything together. And it's just a really easy question. And then, of course, you do the very end bit where you show when it's valid, where you need 5 over 2x to be less than 1, and you also need minus 2x to be less than 1, the absolute value of, which, of course, is just the same as the absolute value of 2x. And then you just compare these two results. This is more restrictive. So you just take, sorry, this is more restrictive, of course, less than 0.4 rather than less than 0.5. So you just take this one, and that'll be that on. Good. So there's something in FP1 called T-formulas, and T-formulas are just super OP. All you do is you say let T equal tan theta, and you can just write down for 4 marks that sine of 2 theta is that, and cos of 2 theta is that. Of course, there's a derivation of that, but in FP1 you don't have to write that derivation every single time you use this. So okay, I'm just going to write this down as if I was in that exam. Usually you write tan theta over 2 and just do sine theta and cos theta here. But because of these two things here, it's much easier for me to do it this way. Just take these results here and replace them into here, like this. You could, of course, factorize out 1 over 1 plus t squared from everything here. Of course, this 1 plus t squared here comes from the fact that this 1 could be written as 1 over 1 plus t squared over 1 over 1 plus t squared, right? It can just be the thing over itself, then factorize it out, and you get this. And then factorize it from the other things, you get this same kind of deal down here. Of course, this cancels with this down here, which is good. These things all come together very swiftly to make this. You factorize out some stuff from here, and everything cancels very nicely. You get t, which is tan theta, which is the right-hand side, based on the initial definition that we wrote down. And the rest of it, of course, very straightforward. Absolutely use these, by the way, in your actual A-level paper, because they're really cool. And just get questions done really easily. You don't even have to think about anything most of the time. So this is all just tan of 2x, right? Because you've doubled the angle in here, so just tan of 2x. You just solve this. Again, I've done this in the normal way because this question has been sent to the examiner already. So I'm just doing this in the normal way. There are probably interesting ways of doing this, including you could do, and again, I'll leave this as homework for you. You could, from here, use T-formulas to get this done. Like if you defined tan x to be t again, you've got the definition in terms of t for sine 2x, and then you just solve a polynomial, which you'll get, and I'll leave that to you as homework. But like I said, this question's been sent to the examiner already, so we can just skip it from here. Part A, very boring, just using trapezium rule, absolutely no way to make that interesting. So we just get this, very, very dull. Next part though, next parts we've got some chances here. We're supposed to actually integrate log of x all squared between 2 and 4. Now the mark scheme was fairly had a lot of stuff on it. It said, of course, the standard way is to do this times 1 and do integration by parts. It also let you do log of x times log of x and do integration by parts. It also let you do a substitution in here for, u equals log of x, and then do another integral by parts, but with an exponential. So we have to avoid doing any of those things and come up with something even better. And then what I'm going to do is, just in case you're unaware, this is obviously product rule, right? When you have two functions of x, like u and v, this is product rule. And in case you're not aware of where integration by parts comes from, integration by parts is literally just a rearrangement of product rule. You integrate both sides here. The integral of this is just uv, obviously, because the integral and differential just cancel. Integral of this plus integral of that. And then you move one of these over to the other side, and you end up with the integral by parts that most of you are used to seeing. So that's the idea. And what if the idea that we had now was, okay, what if you just did that with 3 things? So this is product rule for 3 objects, and you could prove that this works if you wanted to. I don't really care. You then integrate both sides, and then you could rearrange for one of the integrals, it doesn't matter which, and you end up with your triple integration by parts formula. And that's what I'm going to use on this integral that we've got to do here, because there are three things here, right? There's 1, there's log of x, and there's log of x. So that's cool. Let's use the formula. So let's say that u dashed is 1, which makes u x. So and then v is log x and w is log x. So v dashed and u dashed are just 1 over x, aren't they? And so vw is just x, because that's the integral of this, and then leave these two alone, because that's what this says. And then again, have u again, which is still just x, because u dashed is 1. And then differentiate one of the logs for 1 over x. These cancel, leave the other one alone. This is perfect. This is just integral of log x. And so is this. So that's just minus 2 lots of the integral of log x. Everyone knows that the integral of log x is x minus x, x log x minus x. Have the plus c, because I've pretended we're not doing this definitely. But now we are. So let's do this definitely. Let's put the 4 and the 2 in. It's very straightforward from here. And you just do some power stuff. And it all simplifies out eventually. You end up with this here for our answer. So cool. Bear this formula in mind. I think it's certainly something you should be using if you are bored. Question 12 then, we've got a quadratic. We've been given a bunch of information about it, including that it goes through 0, 3, that it goes through 90 at its maximum point, which we'll just call h, little h maybe. And it also goes through 120, 27. I think this is enough information. Let's just call the quadratic this, ax squared plus bx plus c. Let's put all the information in. So when x is 0, h is 3. When x is 90, h is little h. When x is 120, h is 27. Now that's 4 unknowns, a, b, c, and h, and only 3 equations. So let's get a fourth equation. We know its turning point is when x is 90. So if we work out dh by dx, and then put in x is 90, dh by dx is 0 there, because it's its turning point. So we get 0 equals 180a plus b, and that's our fourth equation. I'm going to clean up all these equations, and the reason how I'm going to do that is I'm going to put all of the a, b's, and c's and h's in, and put all the numbers on the other side. And I think I get this. I've also, of course, got to square out these things. So just verify for me that I'm doing this right. So 0a plus 0b plus c plus 0h is 3, and that's the first one. The second one is going to be 8100a plus 90b plus c minus h equals 0. And the same thing for these last two as well. And we get this. Now, people who do further maths will know exactly what I'm doing here. This looks like a matrix because it's a matrix times a, b, c, and h. So we end up with this. Just putting all the coefficients in the matrix like so, and that equals 3, 0, 27, 0. I can, of course, front multiply by the inverse matrix here of this thing here to solve for this. Use the calculator to find the inverse matrix, which it can do the inverse of 4x4s. So I've just inverse this matrix, put it here, and now expand everything out, and we get a, b, c, and h like this. So our quadratic is just the coefficients with these three things, and then the height, that maximum height, is 30, and we answer the whole question. Next, it's asking us to do the horizontal distance traveled by the ball. So it gets to here when its h is 0. So we need to set big H to be 0 and solve this. Of course, we could just put this in a calculator. That's what the marks team wants us to do. And we've also done this question in a stupid way like this, but it feels against the spirit of the challenge to just give up here when there's something interesting that I could do here. So, of course, I'm going to use the quadratic formula on this. I'm going to use the quadratic formula properly. Ignore that because that shouldn't have come up yet. To use the quadratic formula properly, what we're going to do is we're going to put 3/5 here and then 3/5 squared here. Of course, 3/5 squared times this is that. You can verify that if you want to. So now our quadratic is this times 3/5 squared plus this times 3/5 plus 3 is 0. So the quadratic will be 3/5 is equal to minus b plus minus 4 b squared minus 4ac all divided by 2a, where a is this, b is that, and c is that, because they're the coefficients of my 3/5. So we get this. We can tidy this up a fair bit, expand that out, expand this out. You get this, put those two things together, times by minus 1 over 54x squared, I guess, get over there. This, of course, is rooted to this. We can put those together if we want to. We can, by inspection, see that x isn't 0, so we can get rid of one of those and get this. We can, of course, times by minus 90, and we'll get our two answers. This one's the correct one, because this one is happening before on the other way on the picture over here somewhere. So we get this, and then, of course, just write something there. Good. Question 13. I guess maybe you could write something ridiculous here to get it sent to the head examiner. Maybe. Don't know. Cool. Like, it didn't hit and kill a bird when it was in the air. Something like that. Cool. Anyway, curve C has parametric equation as this. I'm a bit disappointed in myself on this question because I couldn't think of anything interesting to do. I feel like I've done it in a somewhat interesting way, but I don't know whether it's enough to get it sent. I've written it like this. you can split this fraction here and have 4 over this plus this over this, but this over this is just 1. So we get this. Now y is equal to t times that same object. So of course this thing here is just y over t. So we get this. And now we can maybe say x minus 3 is that, just 1 minus 3 is minus 2. We can square that to get this. Remember to square both things here, expand out some brackets and stuff. You get this. And plus y squared gives you this, because you can add the y squared and then factorize out the y squared from here to get this thing here. And now I'm hoping this thing is 4, right? Like I'm hoping all of this equals 4. So I just need to show that this is equal to 4. What I'm going to do is say y squared is 16t squared over this squared. I think I'm going to combine those two things first and then write down the same thing again, because just to confuse the examiners even more, just write down the same thing. It's just playing mind games with them. Anyway, finally, I'm going to replace y squared with 16t squared over this thing squared. This cancels with this a little bit. This cancels with this a whole lot. You end up with this. Y is just this thing here. Of course, this can go down to the bottom. This t cancels with this t. 4 times 4 is 16. So this cancels with that, and you're just left with 4, which is the right-hand side. And we're done. And maybe that's enough to get that sent to the examiner. I'm not sure. For this question here, fairly obvious thing to do would be to take log of both sides before you derive. I'm taking the natural log, of course. I explained earlier. The reason I'm doing that is because now I can do its log of this minus log of this following log laws. And so now when I differentiate, it's going to be 1 over y dy by dx, because of course I'm doing a bit of implicit differentiation there. This derives to that, this derives to that, because of course the derivative of this inside is a half, well this is x to the power half, so it's a half x to the power minus half. And now I can times everything by y, and if I just sort out this stuff, I'm going to hope that I get to this. So putting the y back in, like so. Nicely, when you expand this out, this cancels with that, and then this just becomes this squared, so that's quite cool. Of course, you've also got to do this times this as well, so let's expand that out a little bit there. And then let's bring these two things together. I've times this front fraction, by the way, by 2 plus root x top and bottom to make these denominators match, so now we can bring it together. Now, if you times everything by, 2 root x, I think is probably what I did. Oh no, I wrote the whole thing out again to confuse the examiners further, because, it's just, again, these mind games, they're so important. Anyway, times everything by 2 over root x, both top and bottom, you get this. Now this thing here factorizes, I believe, to 2 plus root x all squared, which PowerPoint didn't write properly, but that's fine. This cancels with this, and you just get 1 over 2 root x, which is what they wanted us to get. And now the challenge ends, because I don't know of any way to do this in any interesting way. How are you supposed to do a proof by exhaustion, interestingly? Like, to get both marks, you just have to do what they want you to do. You just have to show that this is bigger than each of these. Like, I don't know how I could make this more interesting. And I also don't know how I can make this more interesting, because you get 0 marks if you do anything other than contradiction. And this is the only way, aside from 2m minus 1, which the mark scheme covers, this is the only way I know to write an odd number, and you have to do contradiction, so you just have to do this. And I don't know of a single way to get this question sent. So we failed on the last hurdle. This is the last question, and we failed. We did every other question, and I think I got all of them sent. I'm not sure. Maybe I didn't. But I don't know what to do on this last question. So this is just what you do. The first objective, remember, was to get 100%. So we have to do that first and just do this. I don't know how to get this sent. Maybe I should just write a note here saying, please send me to the head examiner because I really want it. I really want you to. But I don't know. Anyway, thanks for watching.